Okay, good morning. Hey, we're going to look at problem 7.1, or example problem, sorry, 7.1 from the book, which is where we are supposed to determine the internal forces in members ACF at point J and in members BCD at K. So what we're looking at is this member here, what's going on at this point right here, and on this one right here. Oops, sorry, that's supposed to be a straight line. At this point right there. So to make it so we can see this, remember, so we're finding it here and here. What are the internal forces going on here? Well, so the first part of this problem is a chapter 6 problem. It's a straight up chapter 6 problem. I was initially going to do it. Quite frankly, I even started recording it, and then it's taking too long to do the chapter 6. So I'm just going to point you to another to go through and look back at the chapter 6 problem. It's chapter 6.5. Sorry, it's example 6.5 from chapter 6, and it's the frame problem where we go through and figure out what's going on. So I'm just going to jump straight to the final answers. We're going to come in here and we have this member right here. This is member EBA, and here we have a force here of 600, and we have a force here at B of 1200, and we have a force here at A of 1800. Okay, and then we have this member here, and at this member here, we have at this point, we have 1800 going that direction, we have 1800 going in that direction, and at point C, right there in the middle, we have 3600, and lastly, we have this last member here, boom, and here we have 1200 coming down here. At this point, this is point C, we have 3600, and then at point D we have 2400. So again, so that's the answers from the chapter 6 problem. We can spend time doing that for the chapter 6 problem, but we're just going to go with the answers from there. So now the whole point is, and honestly, it's kind of like glossing over that's really like probably 80 or 90% of the work right there is just getting that problem. But that's not the point of this chapter. So let's look at the point of this problem. So now that we have those forces, we're supposed to determine the internal forces at these different points, right? And so, for instance, this is point J. There's some amount of force going on there. And here at point K, there's some force going on here. So I'm actually going to do part B first. Let's look at part B, because it's actually, quite frankly, quite a bit easier. And then we'll go back and we'll do part A next. So we're supposed to do in member BCD at K. So let's look at this member right here at this point right there. What's going on there? Okay, so what do? Well, we simply cut it, right? So we're going to come in here, and I'm going to take this side, and I have 1200 newtons coming down here. And then at this point, right there at K, I'm going to cut it. So what do I have left? After I cut it off, I have the axial force, the shear force, and the moment. And those are my unknowns. So now we have, and so on the flip side of that, I can come over here on this side. So the rest of this thing, I therefore have the force going in the other direction, the shear force going in the other direction, the moment going in the other direction, which it's getting harder and harder to write this. It's an M, sorry. And now I have here 3600 and 2400. But I'm going to focus on this side right here, just because it has fewer stuff and makes life easier. So if I just do my first thing, my sum of my forces in X equals 0, it's going to tell me what? So, well, this F is equal to 0. Hey, there we go. There's a nice, easy, low-hanging fruit. Okay, and now let's do my sum of my forces in Y equals 0. It's going to tell me what? It's going to tell me that my V is equal to minus 1200, or V is equal to 1200 newtons going up. Okay, so there's the 2 of the 3. That makes life quite easy. And then let's take the sum of my moments. So where should I take the moments? Well, again, wherever I want. If we take it at point K, then what do we have? We have 1200 times the distance from here to point K, which is defined as, I believe right here, 1.5. So 1.5 So that's going to make it rotate in that direction. So the way I drew it, plus my moment is equal to 0. So therefore my moment is equal to 1200 times 1.5. I wrote this down somewhere. Sometimes it's easier just to type it in. 1200, 1.5 is equal to 1800. And it's going to be, this is a negative 1800, or my moment is equal to 1800 in that direction. So in the opposite direction. So there we go. We have my V is 1200 newtons going up. My force is a big fat 0 because there's nothing in that direction. And there's my moment. So that's the easy one. So now, that's part B. So yay, we're done. We can put a big old check next to that. Now let's look at part A. Now we're looking at this point right here. Excuse me. On this other member. So now let's look at that. So we're just going to do the same thing. So I'm going to draw a little line here. I'm going to do the same thing. I'm going to break this one up right here. So here, okay, so I have 1800. Now when I break this, I'm going to have my force, my V, and my moment. Okay. So quite frankly, the way I did this at first is I wanted to say sum of my forces in x equals 0, and sum of my forces in y equals 0, and sum of my moments equals 0. So that works, and that's lovely. But it turns out it was a bit more work, and the way the book does this, which is really, it ends up being easier, is they redefine, let's define this. Actually, hey, I can use colors. Cool. I'm going to define this as my kind of like x prime, and this as my y prime. So now we're going to do this, but I'm going to do it with respect to those axes. Okay, so let's go through and define this 1800. So basically what we're going to say is sum of my forces in x equals 0, which is true. So therefore, it's going to be F, and then what is the x component of this? So now we're looking at breaking this force into this and this, right? And so we have to figure out the angle. So if you come over here, coming way over here, we have this triangle over here. This is 4.8. This is 5.4. So if this is theta, theta is tangent inverse of 4.8 over 5.4. So it turns out that theta is equal to, what is it, 41.6? 41.6 degrees. Okay, which is lovely. So the way I like to do this, let's look at the 1800, the x tick component of it, right? That's gonna, so I'm gonna erase this because it's got a little bit messy. So we have this 1800 Newton force here. How much of it is in this direction, and how much of it is in that direction? So it turns out that when you do your math, that theta is that theta. So the x component of the 1800 ends up being 1800 cosine of theta, which ends up being, when you plug in 41.6, it's 1345. And the 1800, the y tick, so how much of this force is in this direction is 1800 sine theta. So that works out to be 1196, I believe. Okay, so then why is that important? Because give myself a little space over here. If I do my sum my forces in the x tick, right, and that little is equal to 0, well, I have F is going in the positive and the other one is going in the negative, so this F is equal to 1800 in the x tick, right, which is 1345. So we have 1345, and I guess draw it like in that direction. And sum of my forces in y equals 0 is going to tell me that the V is in the negative. So again, going to kind of the ups equals the downs, right, is equal to 1800 in the y tick, which is equal to 1345. Sorry, that's ugly. Or in that direction. Okay. So it turns out it is easier to kind of, whoa, I just wrote the same number. Sorry about that. This is 1196 in that direction. This is the one we just figured out right there. Okay, so there are my F and my V. We figure out those. That's not too bad. And then the last thing I need to do is figure out my moments, right? And this is one of those ones that you can, do however you want. I'm going to take my sum of my moments. Okay, here, let's take the sum of the moments. Let's make our life easier. Let's just take the sum of my moments at point J equals 0. So what do we have? We have 1800 times the perpendicular distance. So now we're talking about from here to here. And that, lo and behold, has been given to us, which is awfully nice of them. That's 1.2. And that's going to make it rotate at this point. It's going to make it rotate around this direction. So that is equal to m. So m is equal to 1800 times 1.2. So it's 2160. And that is, again, in that direction. That's an arrow, believe it or not. Doesn't look like much of one. So there we go. So this one, part B, is definitely a little bit easier, right? Because there's things just mathematically, it's just a little easier problem. But part A is not too bad. Here, this is part A, right? Where we go through here, we take the sum of the forces in X, Y, and Z, redefining this axis. Redefining this as the X prime and the Y prime axis does make life a little bit easier. It's not necessary. You can go through, I actually did the problem without doing that initially. It's not too bad. It's just maybe a little bit more work. But there you go. That's how you do this problem.